So the last example of application of NLP, we'll be learning about summarization. And so to start with, I think most of you might be familiar with summarization. So given a long document or even a smaller document, you want to, let's say smaller document, you want to summarize it into 3-4 lines, or a longer document you want to summarize into a paragraph. And why do we need it? Because let's say a long document, nobody has time to go through all of it. So you might be you don't have time, so you might be requiring a short summary of it, so that you just go through the summary and get the gist of the document, right? So that's what the use case is. So when it comes to summarization, and specifically in NLP, we differentiate, or maybe we categorize the summarization task into two kind of summarizations, very broadly. And that is called extractive summarization and another abstractive summarization. So as the name suggests itself, and we had seen it, what do we mean by extraction? So given a paragraph, this is a source paragraph, and I want to summarize it, so I will use some of the sentences from here, and I discard some of the sentences from here. I use only, let's say, 2 sentences, I will form this summary. So I'm not generating any new sentence, but I'm just utilizing the already given sentences, but discarding some of them because those are not relevant, let's say, for summarization. We are just selecting some of the few sentences, and we are treating that as a summary, right? So this is extractive summarization. And it doesn't involve any kind of paraphrasing. So you will be verbatim, you will copy the same sentences from the source, right? So no rewriting of the text is involved, right? And it involves methods called sentence scoring. So you might be scoring these sentences. Okay, this gets 0.1 score, this gets 0.8 score, this gets 0.9 score. Sorry, this gets 0.9 score, this gets 0.1 again, this gets 0 score, let's say. So we discard all the low scores, we selected all the high scores sentences, right? So that's what is done. And then you can also do keyword extraction. You can apply graphs and create the graph out of a text, and then maybe some of the nodes which are central hubs in the graph, you can just use them rather than the some children nodes and so on, right? So more highly influential nodes within the graph, you might be using them for summarization. So another form of summarization in the abstractive summarization. So what it says, it's kind of very contrastive compared to the extractive summarization, where we were extracting the information from the text itself. The verbatim sentences were copied, but in abstractive, we are not extracting any sentence or paragraph outrightly from the source, but we are generating new text, right? So you can see this is more complicated, but more useful also, right? So given a very long document, you are not just extracting one of the sentence from here and there, and those are salient sentences, but we are generating a summary which is more coherent, and which gives a kind of a very coherent flow, but also it gives a full-fledged picture of what might be happening in the document, right? And if you want to achieve this, you want to have a deeper understanding of the source. So it requires deeper understanding what is happening in the text, right? It needs to know the context, and you should be good at language generation and paraphrasing, and potentially even incorporating additional context, right? So you might be sure your model should be good at learning these things. So it should be able to generate super well text, it should be able to paraphrase things, it should be able to add more context, maybe learning from other document and so on, if it is a multi-document summarization. Or it could be also just the basic idea is to understand, comprehend the document better, right? Other thing is language fluency, coherence, that we have discussed, that is also super important. If you are generating summary and you're not getting well formed English, then it's futile, right? So it's not worth it, right? So all these things we need to cater to when we are doing abstractive summarization. Okay, very quickly we can go through some of the other categorization of it. You might be hearing them maybe somewhere if you do some other courses and so on. So based on input size, it could be single document or multi-document. So as I told you, given a document, you can summarize it. Given multiple documents, let's say 10 documents, and then also you can summarize it, right? So it's called multi-document summarization. Based on the output also, it could be different. Like you might be generating a summary which is query based. So I have a question, I am giving you a document, I want to summarize related to this particular question, the things from the document but related to this question or topic and so on. And it could be generic, right? So just generate a summary. Based on summarization algorithm itself, it could be supervised and unsupervised. That is pretty obvious. And based on summary content, it could be indicative, informative, right? So more factual, more indicative, just hints are there what might be happening, and then the whole fact is there, right? Based on summarization domain, so it could be journal and domain specific. So as I've told, open-ended, open domain summarization, or closed domain, we can call it. And there is another one is also open book and closed book, which we may discuss in subsequent lecture. Based on summarization approach could be that we have already seen: abstractive, extractive, abstractive, and hybrid. So hybrid involves both extraction and abstractions. You might extract some of the sentences as it is, but you might want to add more sentences to it to explain some of the things in text generation manner. So you might be generating new sentences. And based on the language, like could be monolingual, multilingual, cross-lingual, and so on. And based on the summary type, it could be just headline. So you given a document, I want to just generate a headline. That is also a summary, right? So just one line, TLDR summary. Or sentence level, you want to have sentence level summary. It could be highlights, just the highlights, very crisp summary, or full summary, like full-fledged summaries, where you are not constrained, you are not kind of confining the model to generate a particular kind of summary. So it will give a very generic kind of full-fledged summary. Okay, so very quickly we can go through the typical pipeline of it. So we might have a one source document or multiple source document if it's a multi-document summarization, and we need to pre-process it. You might want to do some transformation, and then some processing is done. Post-processing might be done, and then target summary is generated, right? So you can go through in this slide. Other very pertinent metric that is used for summarization specifically is called ROUGE metric, and they have three types. These metrics have three types: ROUGE-1, ROUGE-2, and ROUGE-L. So ROUGE-1 specifically matches the unigrams from your generated summary and the summary which is given to you as a gold reference to check how good your summary is for evaluation, right? So it will match the lexical, it will do lexical matching. So it will just match how many unigrams are matching. And then ROUGE-2 will be bigrams. So similarly, like bigrams, how many bigrams are matching. But ROUGE-L is very strict, and it says what is the longest common subsequence. So it's not about n-grams anymore. It's about how many words, span of words are matching with the generated summary, with the gold summary, right? So these three we compute when we want to know how good our summary is, generated summary is. So we'll cover a couple of very seminal papers which are related to summarization, and it's a pretty old, comparatively old paper which is using LSTMs, right? So before transformers and so on. So what they use bidirectional LSTM, and they encode different sentences, and then they get encoded representation. It forms the document representation, but they score these. So these sentence representations, so let's say this is sentence 1, 2, and sentence 3, they learn a classifier which classifies whether this sentence is important or not. So 1 is important, 0 is not, S3 is more. So these two sentences will be given to the doc, and this sentence may be penalized, or maybe it will not be added, right? So we'll multiply it with some negative weight, and then you get a document representation, and then you can generate the summary from there, and you can extract the summary. So extraction is also involved, right? And you can also generate. So they said that you can also generate the summary using LSTMs, but they also provide the results for the extractive summary, where the sentences are selected and just clubbed to form a summary, right? and you want more detail, you can go through this Summarization paper. It was a very popular paper, and very quickly we can go through the objective of their model also. So you can see this document representation what they had, right? This document representation what we're getting, they are calling it D. And then specifically their objective, they added some of the terms which are unique. So you can say weight matrix multiplied to the hidden state of the LSTM. This turns out to be content. They treat it as a content, what is currently going inside the LSTM. And then the hidden states multiplied by the document representation with a weight matrix with a dot product, they are treating it as a dot product, right? So they are treating it as this sentence, how important it is for this document, right? So that's why they are calling it salience. So for each sentence, they are getting this salience score. Similarly, novelty. So given these sentences, hidden states, and the non-linearity applied to a sentence representation, which is already a set of sentences which is already there, right? So let's say you calculated sentence 1 should be there, sentence 3 should be there, then sentence 7 should be there. So sentence 2, 4, 5, 6 are omitted. Only these sentences are there in this set Sj, right? So this set of sentences Sj already have some sentences. Now for the particular current sentence, you will compute this to know that whether this particular sentence needs to be added there or not, whether it's a novel sentence or not, whether it is adding a new information already to this set or not, right? So that's what novelty part is. And then they had some other terms which you don't have to worry about, right? So some sort of idea about Summarization, and it was the state of the art at that time. Moving forward, they use BERT, as I have told you, like BERT when it came, and they use BERT for extractive summarization, but also abstractive summarization. So for extractive summarization, I told you that, let's say you want to find for a particular sentence, this sentence is scored S2, S3, whether this sentence should be there or not, this sentence should be there or not, and so on. And you get all the sentences which needs to be there. You form a set and you put it in a paragraph that will become your summary. On top of that, abstractive summarization, where you kind of generate a text, right? So in that, what you need to do, you have a pre-trained BERT summarization decoder, 6-layer decoder. So they use a 6-layer transformer decoder to decode the, as we have seen in natural language generation lecture, you need to decode the sentences. So you need to decode the words and it will form the sentence and so on. So one strategy is just do it. Encode with BERT-SEM and decode it using a transformer decoder. You will get a summary. On top of that, what they did, a 2-stage fine-tuning approach they also applied, where they fine-tuned the encoder on extractive summarization. So they did this first and then they decode using the decoder, right? So these two formats they used, and it turns out that it performed well. On top of that, after some years, maybe a year or so, there is this model came into picture, BART, right? And the difference between the BERT and BART is, so you can see BERT, we are masking some of the words, is exactly 15% of the words, and BERT needs to predict what that word is. So it says B, it says D, right? What GPT does, it's an autoregressive model. So you give A to it, start token to it, it generates A, and then A is given in autoregressive fashion, then it generates B, then B is given. So it's an autoregressive thing. What BERT does, given, let's say, these masked words, BERT, the model doesn't need to predict whether there should be some C here or D here, what should be there. So it doesn't do it. And you can see it's not a mask word, right? So it's a span masking, right? So multiple words are masked here. So, and here there is no word, right? So A and B, there is no word. So, but they added it, right? So they kind of add some sort of noise, and we'll see here what are those noises, right? So they add some noise. And at the decoder side, model needs to figure out the whole sequence, what was the original sequence. So that's what the pre-training objective was in BART. And this pre-training objective is very much suitable for summarization, because it is able to generate the coherent text, but is also able to figure out the context from using these noises, right? So which we'll see. So it is called denoising autoencoder, where we introduce the noise, and then this autoencoder encodes this, and then decoder decodes it. So it's like seek to seek and like fully trained, fully end-to-end trained, right? So that's what we had seen it already. But what is the noise? What is the noise here? So one of them is token masking, which we have seen in BERT, right? Another is sentence permutation. So what you can do, let's say these are sentences A, B, C, D. So what you can do, permute the order of these sentences. So rather than A coming at first, you can say D is coming first, then E, then A, then B and C, right? So like that. Document rotations, you can rotate it rather than permutation or shuffling. You can rotate in other order. So if you see from here A, B, C, D, E, it's rotated, right? So rather than starting from A, they are starting from C and it gets rotated. Token deletion, so you can delete some of the tokens. So rather than making a space or mask here, they're just deleted it. Model needs to figure out whether there should be some letter or sentence here or not, right? So at the word level should be word, or maybe sentence level could be sentence or not, right? And then text infilling, you might add more space to it, right? So you have A, B, and the mask is there, and then you add D, E, there is no space, there is no letter or no sentence in between. Then you add one space, so model, to confuse the model whether there should come up, should be filled something here or not. The model needs to figure out that whether this space needs to be removed or needs to be filled, right? So, and at the end, all these noises, you need to figure out what is the original sequence or sequence of sentences and words, right? And the last model to this, which is again performing better than BART, you can see maybe first result itself. So BART, you are getting for XM dataset, which is pretty common dataset, and CNN Daily Mail is also very standard benchmark dataset. And you can see that the compared to T5 and BART, the Pegasus is outperforming the BART and T5 in both the cases, right? So not very with huge margin, but at least it is outperforming them with some significant gain. So what they did, so they did this, so they did gap sentence generation. So rather than removing a sentence or maybe a span of words and so on, or maybe adding some sort of new noise, shuffling and so on, they removed multiple sentences, contiguous sentences themselves, right? So they also hypothesized that a pre-training objective of such like gap sentences, where you remove some of the sentences altogether, it kind of is very similar to a summarization kind of, it kind of aids to summarization tasks super well, right? So model is able to figure out the context in more longer term, and then that's how model learned the capability to know the nuances and intricacies about the presented document, right? So you can see one of the example here. Before that, we will cover this. How do they replace those sentences? So one of the thing is you uniformly select M sentences and at random and remove it, right? So the example could be this green one. So I sentence selected this and this, I remove this sentence altogether. Another version of the setup they have tried is select first M sentence altogether. So select first M sentences from the paragraph and remove it. And model needs to figure out what those sentences are, right? The last step is very good, and they got better performance with this. Select top M scored sentences according to like computing rules 1 with the gold label, right? Oh, with the rest of the document, right? So let's say given this sentence, we are excited to be co-hosting a major drinks reception and blah blah blah. So with this sentence, let's say whole document is this. So what is the rules 1 score compared to this as a this as a target generated text, and the whole document as a gold reference, right? So what is the lexical matching, how much lexical matching is there, right? So at the end of the day, and based on this you get score, rules score, and they selected top M sentences based on that. Let's say this and this, they selected this, right? So these two strategies they followed, and they outperformed the BERT pretty well, right? So this we have seen multiple examples of use cases and applications of NLP models and NLP techniques. And in subsequent lecture, we'll see some more details about the explainability of the large language models and some of the other NLP techniques. and we'll be discussing more about how to visualize those explainability aspects and why it is important to have this explainability built in your model. Why do we care about explainability? Thank you.